So we've talked about how in a transmission line you can have reflections, but we want to describe this mathematically. So the way we can do that is with the reflection coefficient. And something we didn't talk about earlier is that at a impedance discontinuity, you'll also have a certain transmitted wave, and that can be described by the transmission coefficient. And so what this looks like is you have an incident wave coming in, it reaches the impedance discontinuity. You have a certain amount, you have a certain reflected wave, and you'll also have a certain transmitted wave. And something to be very clear about in terms of your intuition for this, it's not like the incident wave is being split into a reflected and transmitted wave. That's not what's happening. It's like, for instance, it's totally possible that the transmitted wave has a greater magnitude than the incident wave. And I won't go into sort of the derivations for this, but essentially the way that you get the reflected and transmitted wave is because the voltage, if you think of this as sort of the interface between these two, the voltage looking into the voltage like at this point, right before the interface, has to be equal to the voltage at this point, right instantaneously after the interface. And so does the current. The current right before the interface has to be the same as right after the interface. There can't be a discontinuous step change in the voltage or current. But the impedance can have a step change, and that's sort of an issue because the impedance is the ratio of voltage to current. So if the voltage has to be the same and the current has to be the same, how can the impedances on either on immediately to the left and either immediately to the right of this discontinuity, how can they be different? And so the reflected and transmitted wave are essentially they're created in order to make the voltage and current match at this interface. So again, you can look more into that if you're interested. Eric Bocatin has some great books on this subject, and you can probably get them for you can access them for free through the Georgia Tech Library. But yeah, okay, so you don't need to really think too hard about that. So you have a reflected wave and a transmitted wave. What is the magnitude of the reflected wave in terms of the incident wave? And so there's a parameter that describes that. So the voltage of the reflected wave is going to be equal to rho times the incident voltage, when rho is going to be the reflection coefficient. So the value of rho is going to be C2 minus C1 over C2 plus C1. So you can sort of see here, if you have an open circuit where Z2 is equal to infinity, this just reduces, so saying at open circuit, this just reduces to infinity over infinity, which is going to be 1. So if rho is 1, then the reflected wave is the same as the incident wave, same magnitude and polarity as we talked about. At a short circuit, Z2 is going to be 0. So this is going to be negative Z1 over Z1. So rho is going to be negative 1. So again, reflected wave, same magnitude, opposite polarity. And then at a matched line, rho is going to be equal to, well, Z2 equals Z1. So the numerator is 0, so rho is 0. So you have no reflected wave. So that sort of, that works with what we've been talking about. Now the transmission coefficient is going to be V transmitted to be equal to the transmission coefficient times the incident wave. So just T times the incident wave, and T is going to be 2 times Z2 over Z2 plus Z1. And again, this was just sort of derived mathematically from setting the voltages and currents equal to each other and factoring in sort of this reflected and transmitted wave that are coming out from this interface.